Okay. Oh. Okay, our next presenter today is Team 25576 Voyager X from Plano, Texas. They're a second-year team out of North Texas, and in their rookie season, they ranked as high as #2 out of rookie teams in Texas by OPR and reached the regional semifinal, where they received Control Awards second place. They'll be presenting about Robustness, the design ethos that ensures competitive longevity. Okay.
So we're going to be talking about Robustness, which is a design ethos that we've used last season in our rookie year that just helped us be competitive throughout this.
So what is robustness? Robustness doesn't mean that you're the best robot in the field. Rather, it means that when you go to competitions, you don't have to pull out a single wrench or a single screwdriver. It means that in every single game that you play, you know for a fact that your robot is going to work. Even though it might not score the most points in a single game, it has the ability to win games in the long run. And designing with robustness in mind makes sure that your robot is organized and easy to fix when problems occur. In this presentation, we're first going to go over some tips and tricks on building a robust robot. Then, we're going to be looking at some failures that we have achieved. And the reason why I say the word achieved is because failures are learning. Failures are what you learn from. And what's better than learning from your own mistakes is learning from someone else's mistakes. And everyone in here is getting to learn from our mistakes as a rookie team.
So the first part of a robot that's important is obviously the frame, right? That's where all your subsystems are built on. It's how your robot's moving. So there's three main aspects we like to think about. One is symmetry and balance, right? So if one part of your robot is, let's say on the right side, there's a lot more weight. So when you're trying to move forward, it's not going to go in a straight line. And obviously for pathing or when scoring, that's not going to be ideal. So the second thing that we like to focus on is the center of gravity. So robots go super fast when you're trying to score high cycle times. And when you have your center of gravity way higher than your frame of your robot, it introduces problems such as tipping. And obviously, if the robot's tipped, it's not exactly going to score any points. So that's something we generally want to avoid. And the last thing we would like to focus on is triangular basing. So usually a frame would be rectangular, right? And what this can do is when it's moving, it can introduce play into the systems, and there can be a tolerance for how much it moves. So using triangular bracing, you can prevent the different channels or the different poles of the robot from moving, and that's just going to make it more robust in the long term.
All right, moving on, one of our strategies is to spread weight evenly across the robot, as Sonia said before. If the weight of your robot is tilted to one side, then as you're moving forward, you might lean to the left a little more. Additionally, we keep more heavier parts of our robot closer to the ground, as this reduces the possibility of tipping. And if the robot tips, it's going to be very difficult to score. Additionally, we put strong supports for heavy loads, which helps prevent bending of the metal, which comes from cantilevers, which we'll talk about after. Additionally, we add shock absorbers, which can reduce the effect of bumping into other robots in order to protect our robot in general.
So these are some different fastening systems we used this last year. So one of the main ones we used was thread locking systems. So what this is, it's a chemical adhesive that you put into your thread grabs when you're screwing in screws. And what this can do is when the robot's moving around, there's going to be a lot of vibration. And using this adhesive, it's going to keep your parts sticking together, and then they're not going to loosen, right? So the pros of this is obviously it's lightweight. It's just like a little glue, you could say. It's invisible, so you can't see, so it doesn't damage the aesthetic of your robot. And it works with pretty much any screw and nut since it's a liquid, so it'll just fit into any space. And so the cons of this is it requires cure time. So it's not exactly a great fix if you have a match in 2 minutes. And it's not reusable without cleaning. So it can be tricky to get the adhesive out, or it might require some additional chemicals. So the best case use for this is like motors, gearboxes, things that you won't usually take apart when you're in between matches. The second one we did is using double nuts on screws. So this is just, instead of having one nut on a screw, you have two. And this basically puts more force on the first nut to keep the screw in place. So obviously it's cheap. You can buy nuts and screws in packs. But the concept of it is obviously you're having another nut on top of it, so you're gonna have a lot more bulk, and it might not fit into like extremely tight spaces. And then the best case use are like for long shafts in open areas of the robot where space isn't exactly the most valuable resource. The next one is washers. So washers, spring tension keeps the bolt under pressure. So this like reduces the chance of the bolt loosening. So the pros of this is it's small, lightweight. It's just like a little piece of metal about that big. But the cons of this is it can lose tension over time. It's not the most sustainable thing for like multiple months. And it has less effect under really high, heavy vibration, let's say another robot knocks into the match. So the best case use of it is like light mechanisms or non-critical joints. So stuff like your chassis or parts of your linear slides that don't move around a lot. And the last one we talked about was nylon nuts. So these are insert grips and or in threads that prevent the loosening. And again, this is reusable. It's consistent under different situations, but it's slightly heavier and they do take more space than just standard nuts. And these are mainly used for the frame of the robot. So your drivetrain bolts or your structural joints, things that don't move around in a match, but you need to work consistently.
Now moving on to joint stress and redundancy. So to identify, one of the problems that we came across was stress joints, and this is mainly in high torque areas such as the lift base and drivetrain corners where the motors are at. And additionally, some parts that have this issue are shock load zones, which include claws and arms. So again, anywhere that has motors, there's usually stress joints around it. Additionally, we have some help you with this, which includes using multiple screws across plates and backup brackets, which can help strengthen these areas around the motor. And additionally, we avoid cantilever designs as it lessens the structural integrity of the overall robot design.
So for vibration and movement, you have to make sure that everything on your robot is staying together, right? So you have to make sure to factor in all of the vibration and movement that is going on during your matches. So firstly, you have to make sure that the continuous move, you have to make sure to consider that the continuous movement is able to cause wear and tear damage. That means that during your matches, you want to have the ability to quickly swap out certain parts of your robot. So for example, if you have a set of slides, you probably want to have a spare set of slides. So just in case you overuse or tear some part of the slide, you have the ability to quickly unscrew and rescrew this new slide onto your robot. Like Arnav said, you want to have the ability to use these specialized locking mechanisms and joint mechanisms to make sure that your robots can perform under continuous movement and vibration from the drivetrain.
So another important part of designing a robot is modularity and quick repairs. So obviously, we'd like to think that when we're putting a robot to competition, things are going to be great, and that's just never going to happen. So one main thing is using modular systems. So these are systems you can take off really quickly in the robot to repair or replace. So you can see here, this whole slide assembly with our outtake system only have about 4 screws attaching it to the robot, which we use with the fastening devices I talked about earlier. But basically what this let us do is in the middle of a match, if our motor went bad, or if our slide suddenly cut, then we were able to take the whole system off, repair it, and quickly put it back on without worrying about damaging other robot parts or having an unwieldy 30-pound robot to move around while you're trying to fix your screws. And so we use this for all of our systems. So our entire intake system can be taken off in 4 screws. And so as our outtake system, and all of our wires and our control hubs were mounted on one plate that we could slide out if we needed to. So overall, this just made the entire robot replaceable in the inevitable case of the robot breaking or stuff going loose.
So here's the first failure that you guys can learn from. So our slides was a really big point of contention during our season. So a really big problem was our initial slide design, which was also our final slide design, was having metal slides guided by bells. So one of the things that it meant was, one, it was slow, but that's not really what I want to focus on. It's the fact that it would break often and would cause the robot to slow down and often even tip. And that's because when the slides are extended, since they're so heavy and so long, it means that the robot center of gravity that Enoch talked about earlier is now 50. That means that the robot is more likely to tip over. So how do we fix this? Well, we couldn't actually fix this in the robot itself. This is because we had already placed all the slides and programmed a lot of autonomous regions. But this brings me to a bigger thing. So building a robust robot doesn't mean just engineering. It also means programming. You have to have robust code. So for this, our solution wasn't just fastening or changing the center of gravity. Rather, what we did was during our autonomous, we made sure to slow down the robot and make sure that the robot was not tipping over when the slides were extended. This made sure that during a match, these slides were more reliable.
All right, moving on. This is another case study that you guys should probably learn from, and for this one, it's a success. And basically, we use 4 mechanism wheels at 435 RPM, and using cap screws and load-bearing joints, it helped to secure the chassis of our robot so that it didn't break through the entire seat. Additionally, we use Loctite glue 242 motor mounts on the motor mounts so that these joints would not be moved while we were operating the robot. Additionally, as I said before, we like to keep the center of gravity very low so that it prevented tipping and also didn't cause too much stress on the joints. And these resulted in very low drivetrain failures throughout the entire season. Additionally, we use this drivetrain throughout most of our matches, so it helped to prove that this system works and will continue to work the way it should.
All right, thank you all.
You know this slide you mentioned about the joint preload. What do you mean by that?
Is it the fastening systems?
Yeah, somewhere there.
Can you go back? This one or this one?
Go back. Yeah. Second.
Yeah. So what is
What do
your
you mean by that?
so fastening system? So for things like our intake, for example. So for our intake, we had a servo operated intake, right? So this meant that the intake system itself needed to be pretty light. So since it's run by servos, right? So what we had to do was since it's so light and it got affected by vibration so much, what we had to do was we had to implement a fastening system where the actual mechanism that keeps the slides together were more flexible. And the reason why this is because when you're moving a lot, right, you don't want these slides to snap, right? So we made sure that these fastening mechanisms were more flexible and had a little bit more play than the rest of the robot to make sure that these fastening systems don't snap in the middle of the game. So this is one example, yeah.
We have 3 questions online, so let's get some quick answers for those. The first one's from Stuart. If the robot is off balance, what are some ways that it can be corrected while keeping all the original components and functionality?
So if the robot is already off balance, so one thing a lot of teams use and we've used in the past, like anti-tip. So that's some robot code that can detect if the robot's tilting or its scroll pitch or yaw is off. Then it can correct it and then lead it to not being tipped over. In addition, the most simple way to do it is if you have more weight on one side that's causing your robot to tip, then you can put more weight or like a dead weight on the other side to kind of counterbalance that. So that's like, there's like one physical and one programmable version you can do to combat that.
And something else I want to add to that is that to ensure that you don't run into these problems in the future, you have to make sure when you first start building a robot, your drivetrain is incredibly stable and relatively heavy because that's the lowest part of the robot. So if the drivetrain itself is pretty heavy, that means the stuff you add on top of it won't affect the center drafting.
The fastest system thing would be the
I think it's there, you could use some CNC material if it's like a specialized corner, or you could even use some carbon fiber printed material to help raise that. I know you could just attach it from both sides of the channels, and then or there are even some parts on GoBuild that are like standard robot commercial off the shelf parts that you can use to help brace those sides.
from Judson, what methods do you use to secure your wires to your robot?
Yeah, so one thing we use is servo clips. So those are to prevent the servos from disconnecting. So they're these little plastic pieces about that big, and you just slot them in. Another one we use are obviously zip ties to keep loose wires from being cut. And then we also have the tubes that you put your wires through, so nothing like causes separation. That's about it.
Okay.
Perfect.
Again, thank you so much for your presentation.